Good morning, everybody, and welcome to this final day of this program on harmonic mass forms and mock modular forms. Today, Micheal is going to talk about holomorphic projection and theta lifts.
Thank you very much. I'm excited to be here for our very last day of this conference. It's been a wonderful conference so far. As Ajit said, today I'm going to talk about theta lifts. I think just for the sake of simplicity, I'm going to focus on theta lifts rather than holomorphic projection, just to slow things down a little bit. Theta lifts are a very fascinating topic. They're very useful tools. They show up in a lot of areas of the study of modular forms and harmonic Maass forms. And in their most general form, they can relate very general types of modular forms. They give relations between some very general types of modular forms. Because of this huge flexibility that we have within this tool of theta lifts, sometimes discussions of theta lifts can become very complicated very fast. And so for our purposes here, I'm going to try to keep things simple, especially since today is the last day of the conference. I don't think this is the right day for complicated formulas and long, drawn-out calculations. And so what I'm going to do today is I'm going to start off by talking about the basic idea of theta lifts, at least as they relate to the types of modular forms and harmonic Maass forms that we have talked about. And I'm going to talk about 4 specific examples. Again, maybe a little bit of a simplified version of some of these. And then I'm going to talk about how these examples relate to each other. These examples that I've chosen are ones that are important examples. They have a lot of relations with each other, and ones that I expect that some of you at some point will want to use. Okay? So the main idea of a theta lift, we want to start by constructing something called a theta kernel. In order to get there, we need to have a seed for our theta kernel. So let's start with this. Theta lifts. So our the first thing that we're going to start with is a seed. Okay, and we're going to call this some function phi, and this is going to be a function of, well, for the way that we're going to conceive of this, I'm going to have 2 complex variables, and we'll have a vector in here. Okay. Now, what we want to do with this is we want to construct a theta function out of this. Okay. And so we're going to have a theta function, which is going to be, sometimes we use this notation, theta of tau z, or I guess I'm doing z tau, semicolon, and then whatever our kernel here is. Okay? And this is just going to be defined as the sum over our lattice points. For our purposes here, we'll assume that our lattice is Zn for some choice of n. Okay? If I have any general lattice, I can always turn this into Zn, and then maybe I just have to adjust my function phi by some matrix. Okay? And then I'm just going to put the sum over here, z of tau, my vector v. Okay. Now, since I'm calling this a theta function, I need some properties for my seed. Okay? So some of the properties I need here is I need this to be a Schwartz function. Okay? And so again, what that means for our purposes here is it should be smooth and rapidly decaying. Okay? Now, the other thing, since I'm calling this a theta function, that's really sort of suggestive of something else about this, the form of this. I do want it to behave nicely with respect to the Fourier transform, as I always want with a theta function. Usually, that's going to turn into phi having some kind of shape. There's going to be some kind of exponential, say maybe e to the minus pi, and then we'll have some kind of quadratic form for our vector. The quadratic form here is usually going to depend on tau and z in some way. Okay, again, it should be smooth, but maybe that just means real analytic instead of holomorphic or anything like that. Okay. And then maybe I've got some other function out front. We'll call this rho of tau z and our vector. Okay? And this might be some simple function, maybe a polynomial in the terms that show up here, or maybe this has some kind of mollifying factor to make sure everything decays fast enough, but we generally want something like this. Usually for the expressions that we're going to see, or for the theta lifts that we're going to work with, these are usually relatively simple. Okay? Some kind of rational function in terms of tau and z bar and tau bar and the components of v. Okay. What's that?
The vector is taking values in.
Yeah, so the vector is taking values in Zn, some lattice, right? Again, I can always rearrange things so that means Zn for some choice of Zn, but there should be some kind of lattice that we're working with. Okay. I'm writing, a lot of times they tell you sort of separately what the lattice is supposed to be. I feel like if I'm writing it this way and I'm only giving you a dependence on the function, maybe I should sort of make this lattice a little bit more uniform. Okay? But generally, it's going to look something like this. Okay? However, we might tweak our terms, but this is basically what we're looking at. Okay? Now, okay, so these are properties that we want for our seed so that this looks like a theta function, something that we would want to call a theta function, kind of real analytic theta function. But now there are other properties that we want for our theta function itself. Okay? Mainly, we would like this to be modular. Okay, so modular means not holomorphic or whatever, but that it's invariant under one of our slash operators. So modular of weight, let's say k in the z variable, and weight L in the tau variable. Okay, so I do want it to be modular for both of my variables. They can have different weights. Again, there are more general versions of this where maybe I allow some kind of non-holomorphic factors of automorphy or whatever. But for our purposes, making things work nicely for our harmonic Maass forms, we're just going to say ordinary weight K and ordinary weight L, okay, for these two things. Now, the way that the theta lift works, okay, we're going to have a theta lift that's going to be, we can think about this sort of some kind of operator, which is going to take some function, some kind of modular object. So right here, well, let me leave a star here for the moment, where star could be, maybe this is SK, maybe this is MK, or maybe MK bang, or maybe this is HK. Okay, but something modular of weight K, and the result is going to be, let's see, something modular of weight, yeah, input is something modular of weight K, and then the output is going to be, let's say, asterisk instead of star, where again, asterisk is going to be something modular of weight L. Maybe we're in SL, or ML bang, or HL, something like this, okay? And the way that this is going to work, this operator of some input function f, okay, we're going to think about this as a function of the variable tau. This is going to be an inner product of f against this theta function, the theta kernel there. And yeah, okay. And this is all going to be, this inner product is going to be with respect to the z variable. Okay. Now, I'm going to write the regularized inner product. Sometimes the ordinary inner product works perfectly fine. Sometimes to get the space that we want for particular inputs, we want to regularize this inner product. And sometimes, if we really want to be adventurous, sometimes we need to regularize this inner product, again, a little bit more strongly than I did. There are stronger versions of this that one might use. And again, as I've mentioned to a few of you, some of those stronger versions of regularization, you start to lose some of the properties that you might want to call this an inner product, okay? But maybe that's the right thing to do to get a theta lift or something like this to actually make sense, okay? Now again, this is going to be an integral over the z variable. The tau variable doesn't go away, it's still there. Theta over here is a function of the tau variable. It hasn't integrated away. So this is still here. And since this is originally modular of weight L in that tau variable, okay, our output will be modular of weight L in this tau variable. Is that clear? Let me go into maybe our first example here. This first example that I'm going to talk about is called the Shintani lift. Now, the Shintani lift, Shintani constructed this. The point of this, or one of the really big points of this, I believe this is what Shintani was aiming for, was to realize the Shimura correspondence analytically. So the Shimura correspondence tells us that there is some correspondence between spaces of cusp forms. Okay, so we might have, let's say, S of, let's say, 2k and k plus 1/2. Okay, so we've got a correspondence between these. My half integer weight cusp forms, I've got to look at the Conan's plus space. Okay, Nick and a few other people have talked about this plus space. Okay, but there's this relation between these. Okay, Shimura showed that these are isomorphic with respect to the Heck operators as Hecke modules, and Shimura gave an explicit map. It's algebraic. It has to do with the coefficients of our forms. But we have an explicit map between these two things. Okay, so let me write these really quickly. Hecke equivariant and for Shimura, explicit in terms of coefficients. Okay. Now remember, when I talked about Heck operators, I focused on the integer weight Heck operators. I didn't talk very much about the half integer weight Heck operators. The formula for those are a little bit more complicated, but all of the same results as far as the fact that they commute with each other. Okay? The multiplication rule, okay? That's the same between these two spaces, okay? Where I guess I did tell you over here in the half integer weight, all of our Heck operators have square index. Over here in the integer weight, we can have an ordinary index. And so this relation goes from Tn with Tn squared. Okay? And that passes through Shimura's original correspondence. Okay? So Shintani wanted to make this, as I understand how that works, Shintani wanted to make this explicit analytically, wanted to see this as an analytic map. And so what we have here is Shintani's a Shintani theta function, which is our theta kernel here, okay? And so I'm going to write this Shintani sub d here, and d is a fundamental discriminant. Fundamental discriminant, and we should have the property that minus 1 to the k times d is positive, okay? So again, K behaving the same way over here, okay? And so if I'm going up to a weight that's 2 mod 4, then I'll have a negative discriminant. If I'm going up to 0 mod 4, I'll have a positive discriminant, okay? And this expression here, the full Shintani theta kernel, is going to be I'm doing Z then tau. This is going to be V to the K plus 1/4 times the sum over M in the integers. We'll have a Legendre symbol here, D above M, M to the K, and then here's the exponential term. So E to the 2 pi I, and then in here we'll have D M squared tau plus 2M Z. Okay? There we go. Okay. And so this is the Shintani theta kernel that we'll use for this map. Okay? And when we, what's that? Oh, V here? Oh, yeah, sorry, this V, this is not the vector V. This is V is equal to the imaginary part of tau. Yeah. So that goes out front to work with the weight here, okay? Make everything kind of fix the modularity. And anyway, this is what we get. Okay? Does that make sense? Again, you can see up here in the exponential, the M squared tau plus 2mz. Okay, this is basically our quadratic form. It depends on tau. And over here, this is like the bilinear form part of it. I guess I didn't write that over there in my general expression, but usually with our theta functions, we've got maybe that bilinear piece. Okay? And this is just what this is. Okay? Now this one is let's see. So this is again weight K plus 1/2 in the Z variable, and it's weight 2K in the tau variable. Okay. Now the really nice thing, or one really nice thing, there's lots of nice things about this, I can use this theta kernel. The way that I describe this, we would want to do our inner product with respect to that Z variable. Okay? And so if I do the inner product with respect to the Z variable, I can get out something of integer weight. Okay? But I can also do the inner product the other way, with the other variable. Okay? And so this correspondence can allow me to go back and forth, either direction, depending on which variable I do my inner product with. Okay? Does that make sense? Yes? So it's here dependent on that M. But yeah, so this isn't exactly the bilinear form that comes out. I mean, what I mean by that, so you've got to, how do I want to say this? Maybe there's a change of variable in Z that's going to get this to look the shape that you want this to look, right? But this is going to work fairly nicely as it is. Okay? But yeah, a change of variable in Z isn't going to affect this too much, but this is the one that gets us our nice transformation properties, okay, as they're supposed to be. Okay. Okay, so we have this. Another very nice fact about this is if we use the Shintani lift, you actually compute all of our terms of our the coefficients of the modular form that comes out of this. Okay, this realizes Walsh-Burgers theorem. Okay. So Walsh-Burgers theorem tells us, so let's suppose that, so F is an element in SK plus 1/2, okay? And we're going to relate this to a cusp form G in S of 2K, okay? Then Walsh-Burgers theorem tells us that the absolute value squared of, say, the dth coefficient. So AF, so this is the dth coefficient of F, if I write this out as a Fourier expansion, okay? Oh, and I guess I need absolute values of D depending on whether I've got positive or negative here. Okay? I take the absolute value squared of that, okay? This is going to equal some explicit constant times the L value of G chi D at K divided by the Peterson norm of G with itself. Okay? Now this explicit constant, this maybe depends on some normalizations, but maybe it looks like a power of pi or a gamma factor. But the main thing is it doesn't change with our discriminant, and it's non-zero. Okay? And so this tells us these coefficients vanish if and only if the L value vanishes. Right? And so this is a very strong, very useful theorem. Very useful in the study of these modular forms and analytic number theory. And you can see this fall out explicitly from the Shintani-Lift map, okay? Actually doing those calculations. Okay? Yes?
This also tells you that the Ramanujan conjecture in half-integer weight is the Lindelof hypothesis in integer weight.
That is fantastic. I don't study Ramanujan conjecture and Lindelof conjecture, so I will absolutely take your word for it. I believe those things. Oh, on the right-hand side? Oh, yes, I am. So I told you it doesn't depend on D, and I lied there with what I have in my notes. I do need a absolute. What's that? Yeah. So I need it somewhere, either. Sometimes there's different normalizations of how you evaluate this, but I do need it somewhere, and so I should write that there. The way that I have this normalized, I should have that. And now this is independent of D. Yeah, thank you for that. Good. Yes, yep. There's always a plus there. Yeah, this is always from our plus space onward. Now there's versions of this that work for vector-valued modular forms. Okay, and so that can allow us to kind of generalize this away from the plus space. Vector-valued modular forms can be very powerful, and we've talked a little bit about vector-valued modular forms, but I don't really want to go into a more general version of this. Okay? Just understand we do have more general versions of this. Okay, any questions there? Are we good with that? Okay, it's a great lift to study, whether you're studying just the Shimura correspondence just sort of algebraically. This helps us to realize it. A lot of very powerful things that come from this. Yes? Oh, yeah. So actually, I'm going to show you something in just a minute. I'm going to give another lift that relates to the Shintani lift under the Xi map. Okay? And I'll give you a nice commutative diagram. But let me get just a little bit further along, a couple of other lifts, and then we'll talk about that. Yeah, definitely that's something we want to talk about. But in order to talk about relations between theta lifts, I obviously need to have more than one theta lift to discuss there. But yes, you're getting ahead, and that is a wonderful question to ask about. Okay. So the next one that I want to talk about is something called the Borchard's lift. Okay. I'm not going to explicitly write out the theta kernel for that. I'm going to talk about what it does for us and some of the really interesting results that pop out of this. As I talk about this, let me just give you a reference for this. Of course, there's Borchard's original paper. So Borchard's original paper is, it can be a little bit dense. This is automorphic forms on OS plus 2, 2 R and infinite products. Okay, it's a little bit dense, but it's written in very high generality. Okay? It's very useful, very flexible. But especially if you're new to modular forms and harmonic Maass forms, it might be very dense. Again, everything's vector valued there. Another reference that I'm going to talk about that really focuses just on the algebraic side of it and sort of an algebraic realization of maybe a simplified version of this is a paper by Zwegers called Traces of Singular Moduli. Okay. And so Zwegers doesn't deal with theta lifts. He very much focuses just on the algebraic results and how can we realize these using algebraic means instead of the theta lift. Okay. But if you're trying to understand the theta lift, I honestly think it's easier to understand what's happening from Zwegers' perspective, from this algebraic perspective, and then if you actually want to use it in this more general situation, maybe come back to Borchards to see the specific realization of it. Okay? But Zwegers gives a very nice, clear description of at least one very important example of this, okay? Completely algebraically, without our messy integrals or anything like that. Okay. This, by the way, is a paper that is cited over and over and over again. Okay? If you have not read this paper at some point, you likely will as you continue studying modular forms, if you continue studying weakly holomorphic modular forms or moving into harmonic Maass forms. Okay. Borchards' lifts are really beautiful in the fact that they give us infinite product formulas for other modular forms. Okay, so let me give you, again, a simplified version of this. Okay, so Borchards. Let's suppose that f of tau is equal to a sum of, so n bigger than minus infinity, c of n, q to the n, and this is, say, something weakly holomorphic. And we're going to focus on weight 1/2, gamma naught of 4, and I should make this the plus space. Okay. Again, generally, this works on vector-valued modular forms. It works on things with higher weight. You just have to change some of the formulas. But this is a very nice, simple situation where things fall out very beautifully. So Borchards defines this function psi of f, and this is going to have, let's see, it looks like, say, psi f of z here. And what we end up getting here is a coefficient of q out front. So this is c of 0 over 2 plus, there's another term here. I'm just going to call this w of f for the moment. In a lot of the interesting cases, this disappears. But this really depends on the negative terms that show up. It's dependent on something called the Weyl vector of f, but yeah, we're looking at the poles of f. So if you have something that's actually holomorphic, that piece disappears completely. Okay? And then from here, we get this product from m equals 1 to infinity of 1 minus q to the m, c of m squared. Okay? And the result is that this is a meromorphic modular form. I guess we don't have notation for a space there. A meromorphic modular form, okay, of weight c of 0 over 2. So this piece out here, okay, is telling us something here about our weight, okay, and oh, sorry, that's not a 2. That's a 24 there. Okay. No, it's a 12. That's what it is. Okay. Meromorphic modular form of weight C0 over 2, and specifically with divisor supported at Heegner points. Of the discriminants given by these terms in the principal part of our function f. Of discriminant, let's see. So the way that I have this, discriminants, I guess m squared greater than 0, wherever c of minus m squared does not equal 0. Okay, now I missed one hypothesis here. I need these to be integers. Okay. Assuming that I have something with integer coefficients, I can do this and I will get all of this thing. Meromorphic modular form of weight is C0 over 2 for SL2Z. There we go, with each of these conditions. Okay. Now there's some things that we can adjust here. Okay. I specifically picked out square coefficients. Okay, I can replace that with a square class. Instead of just squares, okay, some square class. With maybe some, so we'll say dm squared for some maybe absolute value of d times m squared for some fundamental discriminant d, or some discriminant d. Nope, I do want that to be fundamental. Fundamental discriminant d, okay? And that'll change a couple of things here. Notably, it'll change, the Heegner points that we're looking at where we have a divisor, okay? But this is what we get there, okay? If instead of integer coefficients, I have rational coefficients, okay, well then that'll tell me that I need to maybe take some power of this to get something with that satisfies these properties, okay? But that shouldn't be too surprising, given that, so taking powers of our final result is going to be the same thing as taking integer multiples of our original one, right? Okay. What's that? So the Heegner point, so yes, that is a word that I haven't used. Let's, instead of using that, let's just say CM points. Okay, so Heegner, well, he gave us collections of CM points that connected to discriminants and some kind of Galois relations with them, and we end up getting the whole Heegner divisor, but let me just say this to make it a little bit more simple. Okay, we can be more specific than that, but just for the sake of this. So supported at CM points with discriminants. Okay, so the discriminant of a CM point, so a CM point is going to be something of the form A plus the square root of D, where D is negative, divided by C, something of this form, okay? And I want this to be, this should be the root of some polynomial, say ax squared plus bx plus c, okay? That's my a and c. Those should be integers, and the discriminant of the polynomial should be my d in here, okay? So I have used d. So in this case, yes, I need d to be negative for this to be a CM point. Okay, I want a point on the upper half plane for this to be excited. Right here, of discriminant, CM points with discriminant, yes. What was I writing here? Why did I write m squared bigger than 0? Oh, well, yeah, m squared. So I do want minus m squared. I think I started writing something and got distracted. This is what I mean. I need these coefficients here, these minus m squareds, where I'm looking at these negative coefficients, and where these are non-zero. That's the important thing that I need there. Okay, these non-zero, and so in this case, when I'm just looking at my ordinary square class, of course these are just discriminants in Q adjoin I. Okay, but when I change this a little bit, then I get more interesting classes of Heegner points. Yes, yeah, so starting with weight 1/2 and getting something like this. So this is different behavior. So one thing that I should say about this, the actual theta lift itself doesn't give you psi. What it gives you is the log of psi. Okay, so in Borchard's paper, he calls this phi, and he shows that the divisor are these, well, there are logarithmic divisors, but then he says, well, if I'm seeing logarithmic terms, I'm seeing logarithmic divisors, I should just exponentiate this. And what we get out of this are these beautiful product formulas. And so even though this is what usually comes directly out of the theta lift, this is the part people are usually interested in. Oh, yeah. So let me give an example where we get something of actual half integer weight. Okay? And this is a very simple example, but yes, we can get half integer weight. If you want integer weight, we just need this constant to be even or divisible by 4. Say, okay? But a very simple example is the ordinary theta function. So our ordinary theta function is equal to 1 plus 2 times the sum of q to the n squared, like this, right? And suppose we do the Borchard's lift exactly the way I've described it. There's no Weyl vector there because there's no principal part. Okay? Well, what do we get out of this? Psi is going to equal q to the 1/12 times the product of 1 minus q to the n times, what are my exponents here? I'm just looking at squares, so I'm already picking those up. My coefficient is 2 on each one of those squares. Okay? So what is this function? Somebody recognize this? What was that? Yeah. This is eta squared. Okay? And this is a result that comes out of the Borchard's lift. Okay? Oh, this is weight 1. Oh, you're right. So did I get this constant off? I did. Okay. So I should just have C naught just as it is. Okay. Let's see. So where did the C naught over 2, I was copying this from somewhere. What did they do? They might have, there must be a different normalization that I'm missing. Okay. But you're right. Yeah. So this is weight 1. So the way that I've written this down, this is C naught. So I was simplifying from some other example, and I must have my messed up a normalization. But that's got to be what's correct. Okay. The theta function to eta squared is a very nice, simple example that helps us keep everything lined up right. So that's what we've got there. Okay. Let's see. I have another example here. Let me do this just really quickly. But this is one that comes from Zagier's Traces of Singular Moduli. But in that paper, there is a function. What's that? Oh, okay. So there's this function called F7, which is a weight 1/2 weakly holomorphic modular form. Q minus 7 minus 4119 Q plus 8288256 Q squared, ... Okay? And in this case, when you do the Borchard's product, okay, we end up getting out a meromorphic modular form that ends up having to have a divisor at the Heegner points of discriminant minus 7. there's only one CM point of discriminant minus 7, okay? And so it turns out that this ends up having to equal 1, let's see. This ends up having to equal J minus 3375, okay? So this is what we get out of this. And if we expand this out, you end up getting a q to the minus 1 plus 4119 plus 196,884 q dot 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 dot. Okay, and if you actually perform the calculation, multiplication, this works out very nicely. You'll notice that this 4119 corresponds to this one, okay, and that just corresponds to, well, the C1 term here from this product. That's going to give us the linear term, and then we end up dividing by q. This does have a piece from the Weyl vector. It's just a q to the minus 1 that moves that down. Okay? And so there we end up getting those two. Okay? Again, this example is in Zwegers traces of singular moduli. If you want to see more details on that, that's a good place to look. Yeah? The weight of F7, this is weight 1/2. So this is in M1/2 bang of gamma naught of 4. Okay? Good. And of course, there are generalizations of this. Borchards is all vector valued. Okay? We can generalize this to higher level multipliers. Okay? Most anything that we want. Borchards originally did this in terms of the Weil representation, so that's the easiest to work with. But this is an example of how this simplifies when we're looking just at scalar valued modular forms. This one right here. It is J plus. Right. Yes. It is J minus J of the CM point, which is 1 plus square root of minus 7 over 2. Okay. That value is a minus 3375. This is, did I write, that's a 4. Yes, sorry. And that's in the plus space. So these two coefficients, those are the only two that you need to be able to get this far in this expansion. Okay? In order to get a next term, you'd need the coefficient of q to the 9th up here. Good. Okay. Are we good with that? Yeah.
Trying to understand this divisor supported at CM points.
Yeah.
So that's where the 0 is, right?
Yes. So the divisor here means.
Which it does.
Yes.
Right, at that point.
Mm-hmm.
But I don't see the m squared here. I just see an m. Like q to the minus 7. 7 is not a square.
Sorry. Okay. What did I write? I wrote this wrong. So I want this. Okay. So this example is using.
Is it using d equals 7?
Sorry. That is what I want. C of discriminants minus m squared d. Okay. I've got some. Yeah. Sorry. M squared. What am I doing?
So in that example, you're using capital D equals 4.
Yes. Yeah. That's what I'm doing. So capital D is equal to 1. What am I messing up? You're right. I've got something wrong here.
Your example is using the generalization that you wrote, but the theorem, the way you wrote the theorem, you're assuming big D equals 1.
So
Example seems to be using the.
no. So I am. This is using just the square coefficients. This one does just use the square coefficients. I've got a mistake in my notes about what discriminant this is. Okay. And I can clarify that for you. I can pull up Zwegers' paper really quick, but I definitely have some mistake about what this is. But this is reliant on these terms down here. This one is true. So it will rely on discriminant minus m, where I'm looking at minus m these ones not equal to 0. Okay, discriminant minus absolute m. Okay, this is true. I might be overcounting something, okay, but it will at least be some subset of these ones. Okay, and if I use this generalization, then I need to multiply by d on here. Okay, so this at least is true as it's written. Okay, and if you want to know more details, I'll pull up Zwegers' paper after this, and I'll make that correction. Okay, but this is a good example here. Okay, let's see. Let's move on from here. We've got two of these nice product formulas, really beautiful product formulas for modular forms. Well, I guess just one last thing to point out. The thing that Zwegers finds most fascinating about this and wants to use this for is finding the Hilbert class polynomials, okay, that pop out from Borcherdt's theorem here. Okay? He recognizes, well, if we've got these divisors at these CM points, that means I'm getting Hilbert class polynomials. Okay? I'm getting polynomials in J whose roots are these particular CM points, and Hilbert class polynomials are generally difficult to calculate. Okay? And so he uses this work to show how to calculate Hilbert class polynomials, assuming we already know, say, a basis for this space here. If we know these forms, their coefficients, we can figure out these Hilbert class polynomials just using those coefficients. Okay. Good. Okay, let's move on. I've got two more theta kernels I want to talk about. I'm going to talk about them together because they are connected in a nice way. These lifts are called, so the Kudla-Milson lift, and then there's also the Milson lift. Okay, the Kudla-Milson is, I think, is more well known, more well studied than the Milson lift, but they have nice connections, and so, like I say, I want to talk about them together. For these lifts, we're going to let, I want two discriminants. Let's say capital E is positive and delta is negative, okay? And I want these to be fundamental discriminants. Fundamental discriminants, okay? Then what we're going to have here is the Kudla-Milson lift. So let's say Km. This is going to depend on a positive discriminant here. And this is going to take us from, say, harmonic modular, harmonic Maass forms of weight 2 minus 2k. And the result is going to be, say, a harmonic Maass form of weight k plus 1/2. And then we have the Milson lift. This is going to depend on a negative discriminant here. And this is going to go from h of 2 minus 2k, and the result is going to be something in h of 3/2 minus k. Okay, so I have this. Now you might notice these two weights are dual to each other. What I mean by that, if I take this weight and I do the 2 minus k thing, I get down here. Okay? So this is dual in terms of these weights. We've talked about our weights 2 minus k up to weight k. C goes between those. dk minus 1 in the integer weight case goes between them. Okay? I don't have dk minus 1 to relate these here. Okay? We do have C, which we'll see in just a minute, but C isn't really the right relation here. But somehow they are very nicely connected. What these give us are, so coefficients of the lift. So if I have, let's say I have F, some harmonic Maass form here, in h of 2 minus 2k, then the coefficients of, let's say, kmd of f, okay, they're going to look something like, this is something that we've seen before, but these are CM traces. So basically, you're going to take your modular form, or our harmonic Maass form here. We're going to raise it up to weight 0. So we'll use a, so k minus 1 starting at 2 minus 2k of f. So this raises it up to weight 0. And then we're going to evaluate it at these CM points. I'll write what we're summing over in just a moment. Okay. We're going to weight these by some kind of genus character here, dependent on the quadratic form. Okay, I'm not going to talk about what a genus character is, but again, we've seen sums like this in some previous talks this week. Well, yes, Ken's talk, and then also yesterday, yeah, great. I'm sorry, I can't remember your name. Well, yes, Balesh's talk. Okay, and so we have these raises, and then we might divide these by the square root of a discriminant, and then we might also have, there's one other little normalizing factor here that's usually, I'm going to call this W of Q. This is usually 1, okay, but sometimes it's 2 or 3, okay, depending on our quadratic form. This really is counting the number of roots in our field, okay. And then we're summing over quadratic forms Q in our set of quadratic forms of discriminant, let's say d delta, and then of course we mod out by SL2z. Okay, so we're summing over these classes of quadratic forms. Okay, tau q is the root of our quadratic form. Okay, in the upper half plane. Okay, again, since we're summing over classes of quadratic forms, this is going to be well defined up to the action of SL2z. Okay, since f is SL2z invariant. Okay, that'll be nice in there. Okay, but I have a sum of this type. Okay, and these are dependent, notice, on those two discriminants. Okay, if I have my Milson lift, m delta of f, I'm actually going to get the same formula except with a minus sign. Okay, and so what we're looking at here is I do a lift with respect to discriminant d, and I'm looking at a coefficient that corresponds to delta. On the other hand, when I do the Milson lift with delta, okay, the lift depends on delta. I'm looking at a coefficient that corresponds to capital D, but I get the same formula up to a sign that shows up. Okay? So this is a realization of this duality that we talked about that you can see with the Bruinier and Funke pairing. Okay? That pops out here from these lifts as well, the formulas that we get from these. Okay? The same formula, they're just varying in sort of orthogonal directions. Okay? Does that make sense? Yeah. Yes. There are different weights, but they're dual weights. So remember when I talked about this, like this duality phenomenon, this would happen on one side of weight k and the other side of weight 2 minus k. And so we're seeing these dual weights here. Yeah, so basically, let me draw a picture. Again, these coefficients get large, and I don't want to write out a whole lot of coefficients here. But say I start writing out these Kudla-Milson lifts, and these depend on this discriminant d, and so d1, and then a Kudla-Milson lift, say with respect to d2 of f, okay? And I start writing out my coefficients like this, okay, those kind of grids, right? Then if I start looking at those coefficients in the columns of the grid, there I'm going to start seeing these coefficients for the Milson lift, okay, for f, right? And here, this is varying by delta, okay, those columns varying by delta, whereas the rows are varying by d, okay? Does that make sense? Okay, good. Now, all of these lifts are also visible, at least in this one simple example, the case of gamma naught of 4, weight 1/2 and weight 3/2. These are visible in Zwegers' paper. Okay? He doesn't talk about the Milson or the Kudla-Milson lift. He's specifically talking about the Borchard's lift, but when he does his work, he's doing something that is also an algebraic realization of those two lifts. Okay? And he shows kind of how to connect those in a certain way to Borchards' lifts to get this information about the Hilbert class polynomials. Okay. Does that make sense? Okay. So as an example, that function f7 that we just talked about, so this function f7, is it still on the board? Yeah, that one right over there. That is equal to the Milson lift of discriminant minus 7 of j minus 744. Okay. So we apply the Milson lift to this modular function. Okay. In this case, this is where we're saying k, at least for those formulas down there, we're saying k is equal to 1, right? So this is weight 2 minus 2k, that's weight 0. We're lifting up to weight 3 halves minus k, so 1 half. Okay. And this is the form that we get out of it. Okay. So that's an example of that phenomenon there. Okay. Yeah. Yes? Yeah, this is the coefficient, right? So up here from our Kudla-Milson lift, I'm going to need to take this coefficient and I'm going to tag onto it a q to the absolute value of delta, right? Exactly. Yes. Yes. So if I want to put it in this harmonic space, I need to package it this way. This is just the description that falls out from those. But yes, this gives me the, yeah, let me write it this way. So if I call this expression, let's call this expression the trace, so TR sub, let's say delta D of F. Okay? Then the formula here is that I get my Kudla-Milson lift for D of this function F is equal to, so there's going to be a principal part which is a little bit more complicated. Let's ignore this for the moment. Okay, plus the sum over discriminants delta. Okay, now delta is going to be discriminants, so negative discriminants. And then we're going to get this trace of delta df times q to the absolute value of delta. That's what's going to come out there. And then for the Milson lift, okay, again, there'll be some principal part here. In this case, we'll get a sum over discriminants capital D, so positive discriminants. Same trace here, delta df, and then you get a q to the capital D. Now, this isn't quite true either. This is the holomorphic part of these lifts. Okay? That's what we're getting out of this. Okay? The non-holomorphic part leads us to cycle integrals. Okay? Similar, again, to things that we've seen in other talks, and Nick is going to talk about cycle integrals in a minute. What? Yeah, so, well, the main thing to look at is the principal part, but we can get everything if we, well, so I wrote these specifically for fundamental discriminants, okay? In order to extend these to non-fundamental discriminants, really the best way to do that, I mean, to see what you need to get, you write it with a fundamental discriminant and then you use a heck operator, okay? And that kind of shows you how to expand things the right way to get a non-fundamental discriminants. But we can get, at least in these cases, so the Kudla-Milson lift, Kudla-Milson lift and the Milson lift, in both cases, no, I should separate these. So the Kudla-Milson lift will take us from our space of harmonic Maass forms, H2 minus 2k, and the result is going to be our orthogonal space of positive weight. What did I say? This is k plus 1/2. Okay. for the appropriate groups. Okay? It will go to this orthogonal space. Okay? For the Milson lift, this is the one that goes to h of, so 2 minus 2k, and the result is going to go to weight 3/2 minus k, so we're going to negative weight. This is just going to go to our harmonic Maass forms. Yes, it is surjective here. Again, as long as we extend things, I should be, this is the thing, is like you can get everything as long as you take the span over here. It gets a little bit, it can get a little bit messy to go from, there's not a nice clean way to go from a basis over here. We have nice bases over here, we have nice bases over here, and the map doesn't go between those nice bases, right? So if you want to get a nice basis element over here, you probably have to do some work to figure out exactly what form you've got to start with over here. But it is surjective. Okay? Same thing down here. Okay? It is surjective, but you probably have to do some work to figure out what you're looking for. Now, there is one other thing. This is true as long as k is bigger than 1. When k is actually equal to 1, in this case, there's a small thing that can go wrong. Okay? And that's really because of the presence of the constant terms here. Okay? And yeah, let me describe this really quickly. When you apply the Coulomb-Milson lift, and since this is a positive discriminant, let's just go ahead and take 1 there. Okay? And then we're going to evaluate this, we're going to do the lifting of the 1 function. Okay? So what is this doing? This is taking a sum of our, well, we're summing over our CM points, but the function is just 1. So this is counting these CM points. Okay? And so the end result of this is we end up getting Zwegers weight 3/2 Mach modular form that we've talked about before, h of z, which the coefficients are these class numbers. The coefficients of the holomorphic part are class numbers. Okay. Now, if you change this to something that's some positive fundamental discriminant that's not 1, then you end up getting that twisting factor and it disappears. Okay, so that doesn't matter in that case either. It really is the case when our discriminant is 1 and we've got a constant term. Okay, that can play in here. And notice this is lifting something that is weakly holomorphic to something that is not weakly holomorphic. Okay, this is the example where things kind of break. And I mentioned this in my talk yesterday. Things tend to behave very nicely, except with our Eisenstein series, and 1 sort of kind of fits in that definition there for our Eisenstein series. Right around here, this is sort of the boundary of where things behave nicely. And so when we try to do these lifts here, there's sort of this expectation that we might get something a little bit unexpected. Okay? In general, if you do your Coulomb-Milson lifting of the non-holomorphic Eisenstein series, you'll get a non-holomorphic Eisenstein series of half-integer weight. Okay? And then you can see this as sort of a specialization of what we're looking at here. Okay? But that's what we have here. So again, if we generally, and that's this point that I was going to write down here. So generally, I didn't write this down, but generally these lifts are going to go from, so Km and M are going to go from our weakly holomorphic modular forms to our weakly holomorphic modular forms, K plus 1/2 or M of 3/2 minus K. This down here is the Milson. Okay. but this is sort of the one situation where things kind of break down, and it's no longer weakly holomorphic to weakly holomorphic. Suddenly it's weakly holomorphic to harmonic. Okay? And if you start looking at more general things, you can see more general things where you generally expect, so it is almost true that one of these lifts, say the Kudla-Milson lift of F, if I apply the delta operator, whatever our weight is here, okay, this is generally equal to some multiple of the Kudla-Milson lift with delta moving again to whatever our appropriate weight is inside, okay? When we have a 1 that doesn't quite work, basically we're doing some Stokes theorem argument here, and there's a boundary term that stays around when we have this 1. Yes? Right here? Oh, is that what you were looking for? Yeah, yep. Wait, say that again? Yes, Milson map, yes. Milson map down here is the one that's going over here. Kudla-Milson is the one going across the top, right? Okay, yeah. And so this is generally what we have here. Okay, now the last thing that I'm going to say here, again, to connect to our previous things, if I take the Milson map, so let's say phi sub n. So this is the kernel or the seed for the Milson map. And this is, again, going to depend on our discriminant delta. Okay? And suppose I just try my Xi operator on this. Okay? Again, this is going from 2 minus 2k, so 2 minus 2k on my seed for the Milson for delta. Okay? The result turns into the seed for the Shintani map with the same discriminant delta. And so the result from this is that if I apply Xi to my Milson lift of a function f, when this is a harmonic Maass form, okay? Let's see, and then this is 3/2 minus k. The result is going to turn into our Shintani lift, okay, for delta, acting on Xi of f, where this is the 2 minus 2k. Okay, up to some term here. There's always some kind of normalization, right? Okay, but this is how Xi behaves with the Milson. Okay, the Kudla-Milson is going generally to positive weight. Okay, well, anyway, I don't have much to say about Xi acting on that one. But down here, when we're negative weight, this is what we get, okay? So yeah, let me really quickly just draw up this diagram that kind of comes out from that fact, and then we'll stop there for today. So the diagram that we have here is, okay, so h of 2 minus 2k, we move over here using the Milson map to h of 3/2 minus k, and then we move down here using the Xi operator, 2 minus 2k. And this is going to go down, of course, to our cusp forms of weight, let's see, 2 minus that. That's going to go to weight 2k. This moves over here using the Shintani map, Shimura correspondence. And this is going to map over here to S of k plus 1/2. In the plus space. Those are both plus spaces. I guess I didn't write that. I should, everywhere that I have half integer weight spaces, there should be a plus. I'm not going to go back and try to fix that. Just understand everywhere there should be a plus. And then right here, this is our Xi of 3/2 minus k. Okay, and this commutes up to, there's normalizations at every step, right? There's normalizations at every step, but otherwise this commutes. It's also Hecke equivariant. Okay, in the same way that we talked about the Heck operators respect the Shintani map, okay, they respect the Milson map, okay, and everything goes through. We already know that they respect the Xi map. Let's make those dotted so that it lines up. Okay, so Heck equivariant. Okay, and that's just kind of our nice, pretty picture connecting those theta maps. Okay, so there we go. Those are 4 specific theta lifts. Again, I did avoid a lot of the messy details, but hopefully you're able to get something about the large picture about how they connect. Okay, each of those 4 are, I believe, very fascinating and very interesting theta maps, theta lifts. They're all connected in various ways. With that, I think I'll call that good for today and for this week.
Okay, so thank you so much, Michael. We can take a quick question if there's any.
Okay, so this is the Milson lift. It is going to go. Yes, under the same caveat as before, which means we have to be able to vary the discriminants that we're looking at, and also maybe use Heck operators. Okay, but yes, you can get everything over there, assuming you allow both of those 2 things. So for both the Milson and the Kudla-Milson lift, Claudia Alphes has some very good papers. Certainly there are several older papers, of course. Katrin Bringman and Ben Kane and Larry Rowland have several papers on many versions of each of those maps. Personally, I find Claudia's papers a little bit more accessible than Katrin's papers, but Katrin's are, they're also very, very powerful, and she's often very interested in extensions of these maps to more general spaces. And so if you're interested in generalizations, take a look at her papers. But Claudia has some very nice descriptions of these maps in some of the most basic cases. Yeah, so she has a paper on each of those.
All right, thanks a lot.